Okay, welcome to Biostats content on Chapter 6. This is an introduction to hypothesis testing. So this is a really crucial chapter because we're going to be doing hypothesis testing for the rest of the semester. This chapter is sort of emphasizing the high-level concepts of how we go about this procedure. So remember that statistical inference is where we're making statements about population parameters. That could be the full population, or it could be hypotheses and models that we're making statements about. And we're basing these on data that have some uncertainty and sampling error. So the two major forms of inference we talk about in this class are estimation, which we've seen from confidence intervals and point estimates, and then hypothesis testing. So we're going to start talking about hypothesis testing in this lecture. I should mention that inference is not limited to statistical inference. There is logical inference, and that's a realm in which there's no uncertainties and you have guaranteed conclusions. You have these sort of formal statements that have 100% confidence. So premises is what we call the data and logic, like statements like all spiders have 8 legs, and that you go through some steps and lead to some conclusions that you know with 100% certainty. So if you can sketch that out, organisms with 8 legs of this larger area and spiders fall within them, meaning every spider has 8 legs that's within that larger group. And so logical inference works with things like we have a premise like that, the first premise, all spiders have 8 legs, and you get some kind of secondary premise like, oh, X is a spider. Well, if that's the case, then we know a new statement conclusion, X has 8 legs. Or if we have a statement that says, oh, this organism Y does not have 8 legs, then we know that that is not a spider, guaranteed. But then there are many cases where logical inference completely fails to give you a conclusion. So if you say something like Z is not a spider, we don't say, well, it might have 8 legs or anything like that. We just say there's no conclusion you can make at all. Similarly, if we say some organism has 8 legs, we don't know it's a spider in that case, right? So there's also a case where there's no conclusion. So there's this realm of logical inference where all the premises are 100% certain and all the conclusions are 100% certain. There's a lot of cases where we can't say anything at all. And it's appealing. Logic is definitely a great tool for clear and critical thinking, but in science we almost never have these guaranteed premises to start with, so we have to work in a situation where there's more uncertainty, and that's where statistical inference comes in. So imagine you're interested in a question like, does a fertilizer change the yield for some plant? So let's say you've studied a plant for a long time and the total mass of fruit that you get from an organism is around 120 grams and follows a normal distribution with a standard deviation of like 20 grams. I should have put the grams on there for the standard deviation as well. Okay, so you have a well-studied organism that you know some background knowledge on. You want to know if fertilizer has changed things. So the next few slides I'm going to do go through what you might think is how we test hypotheses. It's sort of my naive approach of how I originally thought hypothesis testing was working before I took a stats class. It's not what we actually do in hypothesis testing, but I wanted you to see sort of what the problems are with the naive approach, and then we'll go on to how we actually do things, right? And so this is what I've showed before on the previous slide. We might say, okay, well, let's make a few hypotheses. One hypothesis, hypothesis X, says no, the fertilizer won't change things. So we're still going to have a mean of 120 grams with some standard deviation, 20 grams. Another hypothesis says, yes, the fertilizer should improve the yield by, let's say, 5 grams of fruit. And so now if we collect some data, we should have a mean centered around 125 grams, right? So those are two hypotheses. You might think, okay, we can test those with data, and we can. We collect some data. Let's just say our sample size is 16, and we calculate the mean fruit mass that we get from those. So notice that these hypotheses are stated in terms of the distribution of the fruits. We'd need to figure out what's the sampling distribution of the mean of those. Fortunately, we've already covered that in Chapter 4. Remember that the sampling distribution has a standard deviation called the standard error that's related to the sample size. It's the standard deviation of what we're drawing from, which was 20 in the previous slides, right? 20 grams here, divided by the square root of the sample size, which I said was 16, so divided by 4, so that gives us a prediction. Now we have the hypotheses in terms of the data that we are going to observe, these y bars. Those two hypotheses predict something about the sampling distribution of that data. And so if we think about what the probability distributions look like for those, here are two normal curves. One's got a mean at 125 and one's got a mean at 120. You might think, okay, well, any data that we observe where the data is better explained by, let's see, what did I call it? I called hypothesis Z was the one with the larger mean. With the red curve here, we have any of these points where the red curve is higher than the blue curve, the data is in some sense more compatible with the red curve. So we might just draw kind of a dividing line and say anything over here we prefer the red explanation, the red hypothesis, hypothesis Z, and anything over there we prefer the blue hypothesis. So if you compare these two hypotheses, the threshold is sort of right in between them, right between 125 and 120 is where the probability densities cross right there. And you would get some kind of threshold like this. Any data that we got over here, as I mentioned, we'd prefer hypothesis Z, and any data in the real world over that was smaller sizes, we prefer hypothesis X. That makes some sense, but imagine we were interested in a different hypothesis, same hypothesis X, but hypothesis W now, and it says, well, there's going to be a very slight effect of the fertilizer, only bringing this up to a mean of 120.5, so only half a gram difference. Well, now the two curves are almost identical. There still is a threshold halfway in between them, and so we'd still have sort of a realm of values that prefer one hypothesis versus the other hypothesis. But the threshold's changed quite a bit. Instead of being 122.5, and now it's 120.5. Or you could even imagine that we think maybe the fertilizer doesn't help this plant, and we lower the yield down to 117. So we go through this exercise again. So this is now hypothesis U. I should have put a U on here. Sorry about that. And now the threshold is 118.5, and now low values tend to make us prefer hypothesis U, and high values prefer hypothesis X. So if we're trying to evaluate hypothesis X, that was the same one, that was blue in all these slides. The threshold's changing quite a bit, and in the two earliest examples, low data values make us prefer X, and in this last example, we prefer U if we get a low mass in our real data. So it's a bit confusing if we try to do this, sort of preferring hypotheses based on just comparing two distinct hypotheses. This naive approach sort of sounds intuitive to me. Go with the hypothesis that has the best probability of giving you the data, but we don't know if hypothesis X is true at all, right? That was one of the hypotheses that was in common. If we don't know that that's true, surely we don't know the correct other hypothesis to test it against. So I went through slides with 3 different alternative hypotheses here, and you got 3 different thresholds. So that's a problem, right? Our threshold for what the data should say, different choices of other hypotheses lead to different thresholds, so we don't know when to prefer which hypothesis. And also the passing the threshold didn't tell us if it was a strong preference or not. So we could divide the space of where our data might fall out and say we prefer one hypothesis over here with large massive fruit and another hypothesis with small massive fruit, but it doesn't say anything about the strength of preference. And so for instance, in this example where there was a very slight effect of the fertilizer, any value over here that you observe, sure, it's a little bit more plausible under the red hypothesis and the blue hypothesis, but they're almost identical to each other, so it's just a slight preference. So ideally we'd want a hypothesis testing procedure to be tunable in terms of whether there's really strong evidence or not. And so those are all problems with a naive approach. That's not what we do. As I mentioned, the real hypothesis testing approach that we're going to use in this course is kind of an odd procedure. It's called the frequentist hypothesis testing procedure. And we're going to go through these slides numerous times in this chapter, so don't freak out about the density on this slide. We're going to get a lot of repetition here. But it's an odd procedure in that it really focuses on a special hypothesis called the null hypothesis. What we're going to see, and I'm going to walk through this more slowly in the next slides, we're going to state our question in terms of a null hypothesis and an alternative hypothesis. We're going to choose some significance level for the test, and I'll explain what that means soon. And we're going to collect a random sample. That's where we get the data. We calculate descriptive statistics and something called a test statistic from that sample, and then we're going to determine what the p-value for our test is. And the way we do that is we think about what values of the test statistic we're likely to get under the null hypothesis, and how our observed test statistic differs from those expectations. The p-value itself is the probability of observing a value of a test statistic that's as extreme or more extreme if the null were true. And we'll walk through that more slowly in a sec. That allows us to make a decision about the null hypothesis. If the p-value is low, we reject the null hypothesis. And then we answer our original question and report the results. So I know that's a lot. As I say, we're going to walk through this numerous times till you get the hang of it. But in a nutshell, what it boils down to is specifying a null hypothesis. That's really crucial in this procedure. If I just back up a slide, you'll notice that we specified a null and alternative, but all this calculation about the p-value was based on the expectations under the null, and we make a decision about the null. So that's the crucial thing. We're going to specify a null hypothesis, and I'll explain what that is in a second. We're going to decide what our threshold for rejecting the null is. If the data is really implausible under the null, we're going to reject it. And this alpha parameter, called the significance level, that specifies how implausible the tolerable data is. Then we're going to compare the real data to the distribution under the null, and we reject the null if the data seems really strange. If that probability of seeing something more extreme is less than alpha. So that's it boiled down into a nutshell, and we see that it really focuses heavily on this null hypothesis. I also wanted to just mention before we go on, there's a lot of jargon in this chapter, but it's jargon that we're going to see again and again in the course. Here I'm just highlighting some of the new terms here: null hypothesis, alternative hypothesis, the significance level, alpha, test statistic, the null distribution, and the p-value. Those are all going to be crucial things to learn in this chapter, and we're going to see them in more detail in the next few slides here. So this is inherently another jargon-rich chapter. Okay, what are hypotheses? Hypotheses are statements about population parameters or model parameters. So they're something that we don't directly observe. Once again, we're making inferential statements about parameters, not our sample statistics. So we're going to use our sample to give us statistics that allow us to test the hypotheses, but the hypotheses are about parameters. And this is a mirror image. Remember also the confidence intervals were also about parameters. We put mu in the middle of our confidence interval for the population mean. We don't make confidence intervals about the sample mean. So bear that in mind. That's a really crucial thing to realize. The sample is obviously important. It's how we test things. But the reason your paper or your study is of interest to other scientists is because of what it says about the broader world, the full population. So we're going to phrase our hypotheses in terms of those populations or models, not the specific samples that we have. Okay, so what is the null hypothesis? I've used this term a few times without fully defining it. It's going to be a very specific statement about the population parameter. We need it to be specific so that we have a hope of rejecting it. It's often a statement that of no effect, like the fertilizer has no effect, or two different forces are independent. It doesn't have to be a statement of no effect or independence, but that's really common. And it's a statement that's made for the sake of an argument. We want to see if we can reject this null hypothesis. It's not necessarily the consensus belief in the field, or it's not necessarily what you personally believe. But there's a tricky line here. It's got to be interesting to know if it were wrong, right? So if you're a physicist, you're not going to do a study about whether things fall if you drop them, like an apple falls. We've known that for a long time, and so that would be totally boring to reject the null hypothesis that a heavy object floats in air. So it doesn't have to be the consensus of what the field believes, but it's some specific statement that you can make and see if you can reject based on real data. And the conclusion is we're either going to reject it or we're going to fail to reject it. We're never going to say we accept it, we have proven it to be true, because we're not dealing in real proofs here. We're dealing with what the data tends to prefer. And so we use this term rejection or not rejection. Okay, and what about the alternative? The alternative represents all the other possible parameter values that are not in the null hypothesis. So it's a very vague statement, open-ended, whereas the null is very specific. The alternative is basically everything else. And it's not really tested in our procedure. We don't reject the alternative or prove the alternative or accept the alternative. We're really making statements about the null here. So it's sort of setting things up so that if you're not in the null, then you are in the alternative hypothesis. And this is how we get around that problem we saw before when I went through the naive example where if we entertained another hypothesis that wasn't hypothesis X, the thresholds and our decisions kept changing depending on what hypothesis we're looking at. And so in our real hypothesis testing procedure, we're going to make one specific statement and then have everything else fall into what we call the alternative hypothesis. Okay, so I mentioned we're going to use a test statistic to make this decision. What is a test statistic? it's just something that you can calculate from the data set. A definition of a statistic is a number usually, but any quantity that you can calculate from real data. So that's what a statistic is. What is a test statistic? Well, it's designed to capture differences between the null hypothesis and the alternative. These two hypotheses have got to make different predictions about the distribution of the test statistics. If they both predict the test statistic has the exact same distribution, then gathering the data and calculating a test statistic isn't going to tell you anything because both the null and alternative agree on that. So we're going to calculate the test statistic from our data and we're going to compare it to the null distribution. That's the distribution under the null hypothesis. The null distribution is just a probability distribution of the test statistic calculated if we assume we have a random data of our same sample size, size n, and we assume that data follows exactly the assumptions of the null hypothesis. So this is kind of a thought experiment. We imagine or we calculate what the null distribution will look like. And once again, we're not explicitly calculating the distribution under the alternative, but it is important that it's different from the null. So for instance, in this example of whether the fertilizer has an effect, we wouldn't use a test statistic that was, if we're interested in fruit mass, we wouldn't calculate a test statistic on the height of the plant because our hypotheses are about the mass of the fruit, and so they wouldn't differ in any appreciable way about the height of the plant. That would be a useless test statistic to focus on. It's going to be something about the mass of the fruit, the mean mass, or perhaps the length or something like that. But if we're focusing on mass, then the mean mass is a very good test statistic to use. It uses all of the data that we've collected. We could use the median mass, but that is not as efficient in using all the data. Anyway, the point is we have some choice about what the test statistic is. The only rules are we've got to be able to calculate from our data, and it's got to be something where the null and the alternative make different predictions. Okay, so we're going to see a test statistic later in Chapter 10 called a z-statistic. This is the null distribution of that z-statistic, just to give you a sense of how we use a null distribution. The null distribution is predicting different values of the test statistic if the null hypothesis were true. And what this probability distribution is saying, it's a continuous parameter, so it's a probability density in this case. It's saying values up here near close to 0 of the test statistic. Those are exactly what the null hypothesis predicts, and we wouldn't be surprised if the data falls in here. That gives us no reason to doubt the null hypothesis. But if we get some data values out here near 3 or something like that, those are very unusual according to the null hypothesis. And so those, if we observe data out there, we would suspect that maybe the null hypothesis is not true. All right, so we've mentioned that the way we'd make the decision on the null hypothesis is by calculating something called a p-value. I went through really quickly what a p-value is, but this is using my huge text here to really emphasize this, because a p-value is a strange concept, but it's really important that you understand this for the course. So the p-value is a probability of getting a value of a test statistic that is as extreme or more extreme than the observed value if the null hypothesis were true. Maybe there should be a comment here. So there's several things you need to highlight out of there. One, the p-value is a probability. That means it should always be between 0 and 1. Giving us a negative p-value or a p-value greater than 1 is a sure sign that you don't know what a p-value is. So make sure you have in your mind that it's a probability. It's a statement about what's the probability that you would get a value of the test statistic that is as extreme or more extreme than the observed value. So we're going to calculate some value from our data, that's the observed value, and we're going to compare that to the null distribution and say what's the probability of getting values that are as extreme or more extreme. When we say more extreme here, we're talking about more extremely different from what the null predicted. And remember, we're comparing them to the null distribution. That's the distribution of the test statistic if the null hypothesis were true. So if you're asked for a definition of the p-value, all of these things have got to be in there. It's got to be a probability statement about the test statistic, and in particular, the values being more extreme under the assumption that the null is true. Okay, so for instance, in that example of this distribution I showed before, if the test statistic we calculated from our data was 1.5, that's not very close to 0. We would say 1.5 is pretty extreme. Everything out here is more extreme, so those areas in red here contribute to the p-value. It's things that are greater than 1.5, greater than or equal to, but it doesn't really matter because it's a continuous probability distribution. But also notice that negative 1.5 is also as extreme in the sense of being as different from the predictions of the null hypothesis, right? And that's why this tail of the distribution is also filled in. So the p-value would be the sum of the areas in both of these regions that are shaded red, right? And we use that to assess, is the data really different from what the null hypothesis is predicting? If the p-value is very large, we're including a lot of the distribution, and our data is not that odd under the null hypothesis, so we tend to not doubt the null hypothesis. Okay, let's work through an example to make this more concrete and just reinforce going through this terminology. So this is taken from some slides by the author of your text. The hypothesis is like, does wearing a red uniform help a wrestler win? And so you might imagine a lot of animals use red coloration in aggressive displays. Perhaps that carries over sort of psychologically in human interactions and in sports and things like that. So this was actually a real paper. I'll see if I can find it and put it on Canvas for you. The experiment was motivated by this biological question, setup and question. So does red influence the outcome of wrestling? They also looked at taekwondo and boxing, so various sports where there's just two competitors. The shirt or jersey color was randomly assigned, and they watched 20 rounds of competition at the Olympics where the shirt color was randomly assigned. In 16 of the 20 rounds, more of the red-shirted athletes won than the blue-shirted athletes. Okay, so that's the data. All right, so if we walk through our recipe for how we do hypothesis testing, I'm going to walk through the steps I outlined before. Step number 1, state the question in terms of a null hypothesis and an alternative hypothesis, and choose a significance level for the test. We often choose a significance level to be 0.05. We're going to talk about that more in the next lecture, but let's just right now take that for granted. Okay, so the null hypothesis, remember the null hypothesis should be about the population. We should say that red-shirted and blue-shirted athletes, a good null hypothesis would be something like they're equally likely to win. Is there anything interesting going on here? And so the null hypothesis is saying no, red and blue are independent of the probability of winning, so you should see an equal number of rounds where each wins. Put it in slightly more mathematically, we can say the population proportion of those rounds is 0.5. Sometimes we'll denote that with p sub 0, meaning just like there's a 0 there under the null, to emphasize that the null hypothesis is hypothesizing the value of this population parameter of 0.5. So a big warning here, this lowercase p is the standard notation for the population proportion. In this case, it's the proportion of rounds of majority redshirt wins. I mentioned that population parameters are often Greek letters. That's an exception here, unfortunately. That would be the letter pi, which has other mathematical uses. And this p is completely unrelated to what we call the p-value. So this is really confusing. I wish we could avoid this, but this is just, the way statisticians frequently do this. So this lowercase p, we're gonna have to be careful in these examples. The lowercase p is just referring to the population proportion here, okay? All right, so with that caveat, there's our null hypothesis. What's the alternative hypothesis? I'm sorry, this should say A. The alternative hypothesis, remember the null is very specific, one particular parameter value, and the alternative is just everything else. So it just says that they're not equally likely to win. The population proportion is not equal to 0.5. Okay, so remember both of these hypotheses are stated in terms of population parameters, and the null has to be really specific. And the alternative is usually anything other than the null. Okay, so next step 2 was collect a random sample. The researchers did this. They have a random sample of 20 rounds that they observed and calculate descriptive statistics and a test statistic. So the data was 16 wins. You could use that as a test statistic, or you could also use the proportion of wins. 16 out of 20, that's 80% or 0.8 in terms of proportion. That is an estimate of the population parameter, so p hat. And remember that little hat symbol means an estimate of. It's a sample proportion, not the population proportion. We could use either of these as the test statistic in this case, and we'd get the exact same results. So we're going to focus on using X as the test statistic, but we could actually do this in terms of the proportion. Later in the course, we'll use different test statistics, and it really will matter, and we'll talk about those decisions. But right now, we can use either of these. Okay. Step 4 is the complicated step of the procedure. We have to determine the p-value for our example. What are the values of the test statistic that we would expect under the null hypothesis? How do the observed test statistic, how does it differ from those expectations? We're going to compare the test statistic to the null distribution, and we're going to calculate the p-value. Once again, that's the probability of observing the value of the test statistic as extreme or more extreme. If the distribution we're using to calculate that is the null distribution, so it's one that assumes the null is true. Okay, so let's walk through how to do this. We're going to skip some of the math on this example. Next chapter we'll talk about how we do the math for this, but at this point we're just going to give you the numbers. Here is the null distribution. So this is where I haven't shown you how to calculate the heights of these bars, but we're going to see that in chapter 7, so don't worry about that. So as you might expect, remember the null hypothesis was hypothesizing that the population proportion was 0.5. So there were 20 rounds, and so 0.5 times 20 gives us 10, and that's the highest. That's the most likely outcome. But of course, it's a random sample, so even if the null were true, sometimes you'd see 11 wins or 9 wins, or you might quite plausibly see 12 wins or 8 wins, etc. So this is the full probability distribution. If we were to add up the heights of all of these bars, we'd have a probability of 1. So this is the probability distribution for our test statistic. It's the probability assuming that the null is true, hence it's the null distribution of our test statistic. So this allows us to say, what values seem plausible according to the null. We know we have a limited sample size, so if we see 11 rounds where the redshirted athletes win, that's pretty close to what we were expecting. We probably wouldn't want to reject the null hypothesis if it was just that, just 11 instead of 10. That would happen very frequently, even if the null were true. So what we actually observed was 16. So the way we'd calculate the p-value here is we'd say, okay, well, this is as extreme as what we saw. We actually saw 16. 17 would be even more extreme, as would 18 or 19 or 20. But if you think about it, 4 would be just as far distance. So the distance from 16 to 10 is 6, but also in this direction, if we walk 6 steps, that's just as extreme as what we actually observed, as is 3 and 2 and 1 and 0. So those are the values of the test statistic that are as extreme or more extreme than what we actually observe. So if we add up the probabilities of these outcomes, then that will be our p-value. So that's how we calculate the p-value. In mathematical notation, we're summing up the probability of all of the outcomes that are as extreme or more extreme than the observed value, right? That's the observed, that's what we actually saw based on our real data. So that's where the real data works into this. So in this example, it's the probability of getting 16 or 17 or 18 or 19 or 20, or the other side, the other tail of the distribution, 4 or 3 or 2, or this should say 1, sorry about that, and this should be 0, right? So where does that 4 come from? Once again, the expected value under the null, that's a little funky notation for the expectation of the value of x given the null, is the sample size times the population proportion under the null. So that's 20 samples. Under the null, we expect half of them to have the redshirted athletes winning the majority of matches. So that gives us 10. So that's the expectation under the null. Our observed value is 6 above 10. That means 6 below 10 qualifies as extreme as what we observed. So 10 minus 6 gives us 4. So that's how we figure out where to start counting on the other tail of the distribution. Okay? So we need to sum up all of those values. We're not going to show you how to calculate these numbers until next chapter. This one again is 1. But these are the numbers. And what because of the symmetry in this, you shouldn't be too surprised, or maybe you're not surprised to see the probability of 16 and the probability of 4 are equal to each other, and 17 and 3 are equal to each other, and 18 and 2. Anyway, there's a lot of symmetry here, but overall we get a p of 0.012 or 1.2%. So a very small p-value. It seems really unlikely that we would get a value of 16 or more extreme if the null were true. Now we make a decision about the null hypothesis. If the p-value is less than alpha, we're going to reject the null hypothesis. If not, then what we say is we do not reject the null. So in our example, p is less than alpha. Remember I said we're just going to assume that alpha is 0.05. We'll talk about that next lecture. So that means we're going to reject the null hypothesis, right? If whenever the p-value is less than alpha, we reject the null. We don't say it's disproven. It's possible that the null is correct. There's sampling error, but the jargon we use is we reject it, or we say it's statistically significant deviation from the null. Okay? And now we have to answer our question. It's really important that you be able to put all these calculations into words and into terms of the real biology that you're addressing. We want to report the conclusion in words, and we want to include several things: the sample size, the descriptive statistics, the test statistics, the p-value, what our decision is about the hypotheses. If we reject the null, then we want to say in which direction the data deviates from the expectations of the null. Right? So in this example, we might say, okay, shirt color was assigned at random for a sample of 20 rounds of competition between blue-shirted and red-shirted athletes. In 16 rounds, the red-shirted athletes won more competitions than the blue-shirted athletes. This proportion, 80%, was higher than the expected value of 50% under the null hypothesis that shirt color has no effect. The difference was statistically significant. P-value is 0.012. Okay? So just highlighting all those things that I said your conclusion should include. We've got the sample size in there. We've got our test statistic and descriptive statistics. We rejected the null, so we say the proportion is higher. That's the direction of the deviation. I didn't explicitly say reject, but saying it's statistically significant is equivalent to that. Saying the difference from the null is significant. And then I reported the p-value. And that p-value is associated with the decision to reject. So you can either say we rejected the null p-value, or you can say the difference was statistically significant, and here's the p-value. So you want to group the information in a logical way as well. Okay, so that's one example. We're going to work through another example in the next lecture, and also talk a little bit about the terminology and the types of errors that we can make when we do this sort of hypothesis testing.